This is SpaceTime Series 25, Episode 88. Coming up on SpaceTime, another new record for the most distant and earliest galaxy ever seen. Planet Earth sets its own new record for the shortest day ever. And a gamma-ray burst captured for the first time in millimetre wavelengths. All that and more coming up on SpaceTime.
Welcome to SpaceTime with Stuart Gary.
Astronomers have just set a new record for the most distant and hence earliest galaxy ever seen, dating back to just 250 million years after the Big Bang, some 13.8 billion years ago. It's the latest in a series of discoveries by astronomers sifting through the first data from NASA's new James Webb Space Telescope. If confirmed, the new galaxy candidate, catalogued as Sears 93316, sets a new redshift record of Z equaling 16.7. Sears stands for Cosmic Evolution Early Release Science Survey. Redshift is the spectroscopic Doppler effect caused by the stretching of light from objects moving away from you due to the physical expansion of the fabric of spacetime. It's the same as the change in pitch you hear when a train passes you at a station. The findings, reported in the monthly notices of the Royal Astronomical Society, pushes back the cosmic dark ages and the epoch of reionization by hundreds of millions of years. Just last week, astronomers reported the discovery of Galaxy 13, a galaxy located some 13.5 billion light-years away, in the process setting a new record for the furthest and earliest galaxy ever seen. Now, if confirmed by follow-up spectroscopic observations, this week's new discovery pushes last week's discovery back by another 50 million years. The findings are showing that a significant population of galaxies existed far earlier than what our best computer simulations have been predicting. And that's raising some real interesting questions about how and when the first stars and galaxies formed. The new data being revealed by James Webb is helping to shorten the gap to the cosmic microwave background radiation, the faint afterglow emitted some 270,000 years after the Big Bang when the first atoms formed, allowing photons to fly freely for the first time. This is SpaceTime. Still to come, Planet Earth sets a new record for the shortest day ever, and a unique telescope array to study galactic collisions. All that and more still to come on SpaceTime. Well, if the Earth seemed to spin a little faster for you on June the 29th, it wasn't your imagination, nor your heart fluttering. The planet really did spin faster, by about 1.59 milliseconds short of the full 24 hours. In fact, it was the shortest day on planet Earth since scientists first began using atomic clocks in the 1960s to measure the planet's rotation. An average day on Earth lasts 24 hours because the Earth completes a full spin on its axis roughly every 8,640,000 milliseconds. Although that varies by a few fractions of a millisecond from day to day, depending on things such as internal processes within the planet's geology, including friction between the planet's solid inner core, outer liquid core and mantle, winds hitting mountain ranges on the planet's surface, and ocean tides. And of course, the Earth spin's also partially controlled by the Moon. And as the Moon moves further away from the Earth at around 3 centimeters per year, the planet's rotation slows down. In fact, some 1.4 billion years ago, a day on Earth lasted less than 19 hours. However, over the last few years, there have been several occasions when the Earth's spin has been faster than expected, possibly due to a phenomenon known as Chandler wobble. First identified by astronomer Seth Carlo Chandler in the 1880s, Chandler wobble is a polar oscillation over a 14-month period. Chandler wobble normally is an amplitude of around 3 to 4 meters at the Earth's surface, but it disappeared between 2017 and 2020. Natural disasters and weather effects such as El Nino can also influence the Earth's rotation. For example, the devastating 2004 Indian Ocean earthquake and tsunami shortened the length of the day on planet Earth by 3 microseconds. The planet experienced a record-breaking short day on July the 19th, 2020, when the Earth completed a full rotation 1.47 milliseconds under 24 hours. And that record remained until broken by the minus 1.59 millisecond day on June 29th. And July 19, 2020 didn't retain the number 2 spot for long either, with July 26, 2022 reaching a time of minus 1.50 milliseconds. So it looks like time really does fly, and it's flying a lot faster for the Earth than what it should. This is SpaceTime. Still to come, a unique telescope array to study galactic collisions, and one of the most powerful explosions in the universe since the Big Bang, a gamma-ray burst, captured for the first time in millimetre light. All that and more still to come on SpaceTime. Scientists at Macquarie University have unveiled a unique new telescope array designed to search for and study ultra-faint galaxies. Inspired by the innovative Dragonfly telephoto array in the United States, the new Huntsman telescope comprises an array of 10 Canon EF 400mm commercially available super telephoto lenses, the same as those used by professional photographers. The array's been installed in its own dome at the Siding Spring Observatory in far western New South Wales. It's designed to undertake deep sky surveys, providing astronomers with a unique understanding about galaxy formation and evolution, how galaxies form, how they grow, how they engage with structures that surround them, and what happens when galaxies collide. Principal investigator Dr. Lee Spittler from Macquarie University says the Huntsman telescope's pioneering the way in which astronomers see the southern skies by capturing images of the faintest galaxy structures that conventional telescopes simply can't. The Huntsman's ability to observe the remnants of galaxies colliding with each other and searching for some of the faintest and smallest galaxies in the universe will help astronomers better understand the potential fate of the Milky Way in the not-too-distant future. Spittler says it'll be crucial for understanding what might happen with our own galaxy when it collides with neighbouring Andromeda M31, a galaxy even bigger than the Milky Way, over the next 4.5 billion years.
So Huntsman is a new telescope built by Macquarie University that is unique in that it's built from 10 Canon telephoto lenses. It's designed to actually study very distant galaxies and better understand how our Milky Way is growing.
I use those sorts of lenses to photograph trains. They're also used by other people to photograph wildlife. Using them to image things in space, that's a little bit different.
It is, yeah. So usually astronomers, what we like to do is use very large mirrors to collect light from distant astronomical sources. And that's just because you can make a really big mirror and collect a lot of light. The problem with mirrors, though, is that they're not perfectly polished. And usually they have some sort of support structure that means that as the light's passing through the telescope, it's altered. It's not actually preserving the ultra-faint information about the astronomical sources. The cool thing about the Canon lenses is that they allow the light to pass straight through and while also preserving the information contained in that light. So you get a really pristine image, and that allows you to see things you can't see with much larger telescopes that are built with mirrors.
Is this like almost like having a refractor instead of a reflector telescope?
Yeah, exactly. So that's the big difference. So astronomers love to use reflectors, big mirrors these days, but we're using a refractive telescope, which just uses lenses. And so the light is able to focus straight onto the image and actually preserve the faint information that we're after.
And what exactly are you going to be using this new array for?
So there's a few different projects, but the main one that we're really excited about is to try to understand how galaxies go through head-on collisions with other galaxies. The reason why we're interested in this is because our own Milky Way galaxy is predicted to collide with the nearby Andromeda galaxy in about 4.5 billion years. This collision, or we expect it to happen, we have some idea of what will happen to our Milky Way galaxy, but to get a better idea, what we're using Huntsman for is to actually study other galaxies that are going through this process and see how they're being changed, see what's happening in those galaxies to better understand what's going to happen to our Milky Way galaxy someday.
There's the Canis Major Dwarf Galaxy and the Sagittarius Dwarf. They're colliding with the Milky Way right now.
Yeah, that's right. So we do see that galaxies tend to grow by consuming or merging with other galaxies. It tends to be smaller ones like the two galaxies you mentioned, and which you could see in the southern sky if you know where to look for them. But occasionally, and maybe once in an entire lifetime of the universe, a galaxy will go through a big merger. So with another galaxy of comparable size or even much larger. And that will completely change the structure of the Milky Way galaxy and the Andromeda that's going to collide with. So while it tends to grow a lot more frequently from tiny little galaxies falling in, the big event that's going to happen in 4.5 billion years will forever change the fate of our Milky Way galaxy.
There have been some amazing simulations showing what's going to happen when the two do merge. A huge elliptical galaxy will be the result, some say. What's your prediction?
Yeah, probably something that's more elliptical in shape. So currently the Milky Way is a spiral galaxy, a big disk, lots of stars and dust that produce new stars. Same thing with Andromeda. It's about the same kind of galaxy, just a little bit bigger. So I think when the two kind of come together, the rotation in the disks, the two galaxies will all be kind of randomized. And the orbits of the stars that will be left over in the big galaxy will be on more chaotic or random orbits, which will make it look more puffed up like a football or something, elongated footy ball, I guess.
When we talk about galactic collisions, people think of smash-ups, but they're not really smash-ups because there is a lot of space between the stars, isn't there?
That's right. Yeah, it's going to be kind of not a dramatic event. So in fact, it'll take a long time. The merging and the collision, I guess, will kind of be drawn out over probably 5 billion years, where the two galaxies will just slowly kind of mingle together. And you're exactly right. Because they're mostly empty, the distance between our star and the next one is huge, and there's a bunch of empty space. So you can kind of maybe imagine like it's as if two clouds are merging, like there's little water vapor particles in the two clouds in the atmosphere, and some of them will collide, but the two clouds will just kind of be clouds afterwards. They'll just look kind of the same. The bigger clouds, maybe a different shape, and the direction will be a bit different. But aside from that, they'll just be a cloud, or in our case, just another galaxy that looks a bit different.
Is one of the big fears about this collision not so much the stars bumping into each other, but all the gas that will be collapsing as a result of that, and consequently lots of new star birth, consequently lots of new ultraviolet radiation?
Yeah, so when you have two gas clouds colliding, I guess, or like the cloud analogy, while the stars will kind of pass around each other, the gas and dust in the Milky Way and Andromeda won't kind of miss each other. It will actually collide, and it won't be too dramatic, but what it will do is cause the dust to be a little bit denser, and that little bit of density might actually trigger a bit of new star formation, which will indeed lead to some very bright, ultraviolet bright stars to be formed. And if you're nearby one of those, you're in big trouble, because the amount of UV light they put off is significant, and it would definitely impact any sort of form of life that was nearby. So you're right. We probably need to maybe worry more about that. Another consequence, though, might be that you kind of consume the last bit of gas and dust in the Milky Way. So there might be a big event where a lot of stars are formed, but maybe that consumes the most of the gas that's left over. And so another potential outcome is that you have some star formation, but then that kind of is it. You stop forming a lot of stars in the future in the Milky Way.
No, dead and red.
Exactly, yeah. So that might be a problem if you, want to continue living many billions of years in the future, and you need new stars to go inhabit, assuming we're kind of zipping around the Milky Way at that time.
Yes, assuming that the gravitational perturbations haven't flung us off into deep space.
That's true. Yeah. If I guess the sun's, due to end its life around the time we're colliding. But if we're still around, maybe like another star, then indeed we might get unlucky and get slingshotted out of the final galaxy, and you'd have a really long, drawn-out view of it just disappearing and going away, and eventually the night sky would be pretty dark.
Look at the bright side. Maybe the Earth's orbit around the sun will be expanded further out so that we'll get a nice toasty feeling instead of a sizzled up feeling as the sun expands into a red giant.
That could be another outcome, yeah.
You look at other galactic collisions, I take it. You must look at them with fascination.
That's right, yeah. It doesn't happen too often, and I guess the hard part is that you only capture a single instant in time. And so we really do look for the galaxies and kind of use one galaxy that's going through this event as kind of a snapshot, and we kind of produce like a timeline of what happens during the process of immersion. We can kind of take one galaxy and say, this kind of looks like it's just about to happen. And then another galaxy that say, this is probably like half a billion years into the collision. And then another one that's maybe like 4 or 5 billion years after the collision began. And so by doing that, you can kind of piece together maybe a timeline of what might actually happen. But it's hard. So we're really trying to find these colliding galaxies. And what the Huntsman telescope will do is kind of allow us to see the very end stages of that. So we won't get information about the really obvious ones. We'll look for more subtle signatures of that merging process. And that's what Huntsman's really good at, looking at this diffuse light that's coming off the galaxies, of stars being thrown off that galaxy, and look for that kind of signature. So I think that's kind of where Huntsman's filling a niche, looking at the final stages of the collision to see how the stars eventually settle down, see if they're thrown out, that kind of thing. So definitely keen to find galaxies that are going through that process.
Now, so far you've avoided the D word. I've got to ask you, when galaxies collide, there's got to be stuff happening with the dark matter in those galaxies. Will Huntsman do anything in that regard? Will it show us areas of density that are likely to be hosting more stars?
Yeah, I think we can't directly see what's happening with the dark matter, but I guess one way that we are kind of looking for things that are dark is working with radio astronomers in Australia who are looking at dark neutral gas, hydrogen gas. And they're really good at finding this and looking for really faint structures that might be kind of popping out or about to be involved in a collision. So what we'll do is partner with them to look for any stars that are at those locations. And if we find them with the Huntsman, then that's kind of a small mini galaxy. But if we don't find anything with Huntsman, it's actually kind of an interesting thing to find, because in the beginning of the universe, there's a bunch of gas around and probably dark matter. And so you expect that maybe there's some failed galaxies, ones that just didn't have enough density and maybe enough dark matter to actually form new stars. And so maybe we'll get lucky and find kind of these dark galaxies when we team up with the radio astronomers in Australia. So I think that's the main way that Huntsman can help out with that effort, looking for galaxies or proving a galaxy is truly dark. It doesn't have any stars in it.
An area of debate whether or not globular clusters, these are collections of thousands, maybe hundreds of thousands of stars, all tightly packed gravitationally together, whether these things are molecular gas and dust clouds that have all become stars at once and they've just hung around together, or whether they're the cores of galaxies that have already emerged. What's your evidence telling you?
Yeah, so I guess I would say that there's probably a mixture of both. So we do know from observing other galaxies that globular clusters are really abundant in very massive galaxies. We know that massive galaxies formed really quickly in the early universe. They were in a very dense region of the universe, so lots of dark matter, lots of dust, gas, everything you need to produce stars. And they probably collapsed very quickly under the gravitational influence of so much dark matter. And in such chaotic conditions, such dramatic bursts of star formation, you're inevitably going to get big clouds that collapse into a single population of stars. They'll be really dense, and that's exactly what probably produced globular star clusters. So probably the most of the globular star clusters in big galaxies like that are from that kind of formation. But we also see smaller dwarf galaxies that have these nuclei. They're right in the core of the galaxy. There's this really compact star cluster that we call a nuclear star cluster. But when you kind of look at a nuclear star cluster and a globular cluster just floating around the Milky Way, you do see some similarities. So it does suggest that there are probably some globular clusters in our Milky Way and other galaxies as well that were once at the core of a smaller dwarf galaxy. And as that galaxy was consumed and fell into the Milky Way, it stripped off all the stars around the galaxy, except that core was still preserved because it's so dense, it can actually survive something like that. And so that's probably what's produced maybe the more massive globular star clusters in the Milky Way and other galaxies. a really compact bit of star formation at the center of of a different galaxy that's now deposited itself and is now orbiting the Milky Way. So I think there's kind of two paths, and I think we've seen evidence of both of them probably being true, but maybe for the more massive ones, it's more likely that you maybe came from another dwarf galaxy that had a really compact but massive core.
The fact that we only see them in the galactic halo, does that tend to favor one model over another?
Yeah, so that would be the things in the halo of the Milky Way tend to be on orbits, the stars and the globular clusters that are more kind of randomized, more circular and bigger. Things that are in the disk are things that probably formed in that disk. They're rotating around the Milky Way. And so things that are in the halo, they probably, the leading theory is that most of those stars actually, again, fell into the Milky Way from smaller galaxies that it consumed. And so those would have been fallen in kind of random trajectories into the Milky Way. And therefore, the stars that were stripped off that galaxy would have been thrown around in random orbits. And so they then kind of settle in a more randomized, kind of long, round, elliptical orbit through the Milky Way that doesn't really map onto the disk of the Milky Way because they came in a random trajectory that had nothing to do with the disk in the first place. So yeah, that's probably correct.
That's Dr. Lee Spittler from Macquarie University. And this is SpaceTime. Still to come. A gamma-ray burst, one of the biggest explosions since the Big Bang, captured for the first time in millimetre wavelengths, and another joint Australian and American spy satellite launched from New Zealand. All that and more still to come on SpaceTime. Scientists using ALMA, the Atacama Large Millimetre Submillimetre Array Radio Telescope, have for the first time recorded millimetre wavelength light coming from a gamma-ray burst, the fiery explosion caused by the merger of a neutron star with another star. The findings, reported in the Astrophysical Journal, also confirm this flash of light to be one of the most energetic short-duration gamma-ray bursts ever recorded, leaving behind one of the most luminous afterglows on record. Gamma-ray bursts are the brightest, most energetic explosions in the universe since the Big Bang. They're capable of emitting more energy in a matter of seconds than our Sun will emit during its entire lifetime. This gamma-ray burst was catalogued as GRB 211106A and classified as a short-duration gamma-ray burst. These explosions, which scientists believe are responsible for the creation of the heaviest elements in the universe, things such as gold, platinum and uranium, result from the catastrophic merger of binary star systems containing a neutron star. The study's lead author, Tamoy Lasker from the University of Utah, says these mergers occur because of gravitational wave radiation removing energy from the orbit of the binary stars, causing them to spiral in towards each other. The resulting explosion is accompanied by jets moving at close to the speed of light. And when these jets are pointed towards the Earth, astronomers see a short pulse of gamma-ray radiation, what's referred to as a short-duration gamma-ray burst. These usually only last a few tenths of a second. Scientists then look for an afterglow, an emission of light caused by the interaction of the jets with surrounding gas. Only half a dozen or so short-duration gamma-ray bursts have ever been detected at radio wavelengths, and until now, none were detected in millimetre wavelengths. Lasker says the difficulty is the immense distance to the gamma-ray burst and the technological capabilities of telescopes. Short-duration gamma-ray burst afterglows are very luminous and energetic, but these explosions take place in distant galaxies, which means the light from them can be quite faint. In fact, the light from this short-duration gamma-ray burst was so faint that while the early X-ray observations by NASA's Swift Space Telescope saw the explosion, the host galaxy itself was still undetectable at that wavelength, and scientists weren't able to determine exactly where the explosion was coming from. The afterglow is essential for figuring out which galaxy a burst is coming from and for learning more about the burst itself. Initially, when only the X-ray counterpart had been discovered, astronomers thought the burst might have been coming from a nearby galaxy. And a significant amount of dust in the area also obscured the object from detection in optical wavelengths using the Hubble Space Telescope. So we have a bright burst in gamma rays, a fleeting encounter in X-rays, nothing in visible light. In fact, Hubble's observations revealed an unchanging field of galaxies. But then ALMA's unparalleled sensitivity in radio wavelengths, especially in the millimetre area, finally allowed the authors to pinpoint the location of the gamma ray burst with precision. This is SpaceTime. Still to come, another joint Australian and American spy satellite launched from New Zealand, and bits of a SpaceX Dragon capsule dropping from the skies. All that and more still to come on SpaceTime. This is SpaceTime. Briefly in other news, Rocket Labs have launched another joint Australian and American spy satellite into orbit aboard their Electron launch vehicle. The NROL-199 mission flew from Launch Complex 1B at Rocket Labs' Mahia Peninsula Launch Facility on New Zealand's North Island east coast. The mission for the United States National Reconnaissance Office and Australia's Department of Defence is the second spy satellite for the two nations to be launched in 3 weeks, and comes amid rising tensions in the South China Sea, where Beijing has launched what it's calling war games off the coast of Taiwan. The mission, named Antipodean Adventure, had been delayed by several days because of high winds in the launch area. It follows the launch of the NROL-162 mission for Washington and Canberra back on July the 13th. Details of both missions have been kept highly classified.
It's early evening on August 4th here in New Zealand at Rocket Lab's Mission Control Centre as we count down to the 5 p.m. local time launch of this national security mission for the National Reconnaissance Office. Our Electron rocket vertical and ready on the pad at Rocket Lab Launch Complex 1 in Mahia on the East Coast. My name is Muriel Baker. Thank you for joining us for our 29th Electron launch to deploy the NROL-199 payload to orbit. Our first attempt at launching this Antipodean adventure for the NRO was stood down earlier this week due to strong winds, but with much more settled weather today through the launch countdown so far, we are on track for launch right at the top of the launch window, opening at 5 p.m. local time. That's 5 a.m. UTC and 1 a.m. Eastern Daylight Time, or 10 p.m. Pacific if you are joining us from that time zone. Today's NROL-199 mission is the NRO's 4th launch of the year and the second on Electron from Launch Complex 1. It's one of more than a half dozen launches planned by the NRO in 2022 to help provide 500,000 plus government users with intelligence information that enables them to protect the United States interests and support worldwide humanitarian efforts. Shortly, we'll be rolling into the final go, no-go poll for launch. Each flight controller will be asked about their launch readiness by the launch director before we proceed to liftoff. Our launch director has about a dozen go, no-go reports in the poll, and at the end of the poll, the launch director will confirm whether or not we are go for liftoff. Let's bring up the mission control nets now to listen in.
This is the LD on mission, proceeding with the go, no-go sequence stage.
Aegis go.
Avionics.
Avionics, let's go.
GNC.
GNC, let's go.
VCon.
VCon, let's go.
T1.
T1 let's go.
GC.
GC is go.
PLS.
PLS is go.
RSO.
RSO is go.
MET.
MET is go.
MM.
MM is go.
SVMD.
SVMD, go.
LD sub.
LD sub is go.
That concludes the go, no-go sequence. We are go for terminal count. From this time, the 3-word hold procedure is in effect.
So as you heard at the conclusion of the go, no-go poll, we are moving forward with the launch of the NROL-199 mission. Today's mission is our second of 2 back-to-back launches for the NRO from Launch Complex 1. Around 3 weeks ago, on July 13th, we launched the NROL-162 mission from Pad A, achieving a flawless launch and payload deployment to deliver the satellite to orbit. Now, NROL 162 and 199 are the third and fourth missions awarded to us by the NRO under their rapid acquisition of a small rocket contract known as Razor. This approach allows the NRO to pursue the use of both large and small satellites to create a space architecture to provide global coverage to help answer a wide range of intelligence questions. The first two NRO missions to fly under Razor also launched on Electron in 2020 in a showcase of the NRO's capability to deploy missions from spaceports outside of the United States. It's great to be supporting the NRO once again with launches on Electron, this time from two separate pads at Launch Complex 1. NROL 199 will be our third launch from Pad B at LC1 in just over 5 months from when it was officially opened in late February. In fact, in just over the past 5 weeks, we have launched 3 missions from LC1. The first was the capstone mission to the moon from tonight's launch pad, Pad B, followed only 15 days later by NROL 162 from Pad A, and now NROL 199 from Pad B for tonight's launch. Having 2 launch pads, range assets, and mission integration facilities for our own exclusive use within the same spaceport makes back-to-back missions like our 2 NRO Razor launches possible. To start with, we can run concurrent campaigns at LC1 thanks to numerous clean rooms and plenty of room in the integration hangar for multiple rockets. 2 launch pads equal double the opportunity when we don't have to wait for a single pad to be refurbished between launches. And if customers' missions need extra time and attention, we can keep the rest of Electron's manifest on schedule by proceeding with the next launch. So even with just 1 pad at Launch Complex 1, Electron became the second most frequently flown US rocket annually, and with 2 pads at LC1 and our third in Virginia expected to come online by the end of the year, we are excited to see what Electron can do with 3 pads across 2 continents for faster and reliable access to space. Today's launch will be our 29th Electron launch, but in the not-too-distant future, we will be taking to the skies with a different rocket, one that's more than twice as tall as Electron, more than 3 times its diameter, and capable of lifting more than 40 times the payload mass that Electron can lift. That's right, we are deep into the development of our Large Neutron rocket. Designed for larger payloads, constellation deployment, and even human spaceflight, Neutron is a new breed of launch vehicle with reliability, reusability, and cost reduction hard-baked into the design from day one, like carbon composite structures and designs of the future, like our Hungry Hippo fairing design. Recently, we broke ground in Virginia on the production complex for Neutron, and work continues there at pace. The 250,000 square foot production complex is being built on a 28-acre site near the NASA Wallops Flight Facility and Mid-Atlantic Regional Spaceport on Virginia's eastern shore. Neutron's first pad will also be located there, close to the Launch Complex 2 pad for Electron. Every launch, before we roll out to the pad and get ready for the mission of Electron, each Rutherford engine goes through a rigorous test campaign. Each of these engines, and in fact each of their components, go through extensive quality assurance tests at our propulsion test facilities. Each pump and motor controller goes through a flight-like acceptance test on our test rigs before they are assembled to a Rutherford. And then each engine must first pass a bench test before moving through 2 hot fire tests at one of our engine test cells. Finally, once the engines are assembled into the 9-engine configuration we call the power pack, the entire first stage and its engines are tested. We call this a stack test, and this process is in fact repeated for stage 1, stage 2, and the Curie engine module on our kick stage. Running our engines at least 3 times before launch is one of the many ways we drive mission assurance with Electron. Let's hand it over to our launch director to take us through the final reports from mission control operators and lead us into the 10-second countdown to liftoff.
Flight computer ASGOs are green.
Confirmed ASGOs are green.
Beacon, lock auto sequence and confirm.
Confirmed locked.
All operators, this is the LD on mission. We are go for auto sequence. Start. LD is go for launch.
AVBs on internal power. AFGS is green and enabled for flight. Vehicles fully on internal power.
Clock load complete. System in recirculation. Anti-gas ring disabled.
Stage 1, Stage 2. Rest for flight.
High flow engine purge enabled. Deluge is activated.
10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. And we have liftoff.
Vehicles pitching over.
Stage 1 proportional is nominal.
HVB discharge looks nominal.
Entered burnout detect mode.
There we go, T plus 50 seconds into the NROL 199 mission on its Antipodean adventure. Electron's engines will soon power down slightly to prepare the rocket to pass through max Q, or the point of maximum aerodynamic pressure against Electron during launch.
Cleared max Q.
Stage 1 propulsion is nominal.
And Electron has passed through max Q, the rocket's first major test after leaving the pad at Launch Complex 1 on the coast. Electron's 9 Rutherford engines are firing hot as they burn through the first stage's tanks of liquid oxygen and RP1 propellant. T plus 1 minute and 42 seconds, and Electron's trajectory is also looking good. The rocket is at now over 30 kilometers above Earth and moving quickly at nearly 4,000 kilometers an hour.
Seconds to MECO.
MECO confirmed.
There you heard it, all three events happening back to back through MECO, stage separation and second stage engine start. Electron's second stage continuing nominally for the NROL 199 mission. Soon it will shed its payload protective fairing to lose the unnecessary weight now that the vehicle is in space. In fact, there it goes, so the payload fairing has split in half and fallen away. The NROL 199 payload is now exposed to space in preparation for payload deployment, and Electron's second stage is continuing to orbit, carrying the kick stage and the payload. Everything continues to look nominal, with the Rutherford engine glowing bright as it powers the mission on. The burn of this engine lasts for about 7 minutes to help bring the payload closer to its final orbit before we have a second stage separation that enables our third stage, known as the kick stage, to carry on with the rest of the mission. Our kick stage is critical in delivering the NRO the exact orbital insertion they need for this national security payload. With its own reliable Curie engine, our kick stage can be maneuvered precisely to achieve pinpoint orbital drop-off of the NRO's payload. That payload deployment is expected to take place around an hour from now.
Stage 2 propulsion still nominal.
Coming up to T plus 5 minutes and 9 seconds, and Electron's stage 2 engine continues to fire nominally along our expected trajectory, ready to deliver the NRO payload to space. We are about 1 minute away now from our next mission milestone, the swap of our rocket's batteries, providing electric power to the stage 2 Rutherford engine. So the Rutherford's electric fuel pumps use electricity rather than a pre-burner to operate. But once the batteries are drained, we don't need them anymore. They become unnecessary weight on the second stage, so they're discarded when we swap to a fresh new one that keeps the engine running. This is our battery hot swap event.
Throttling down.
Approaching hot swap.
Go right on time. We have had battery hot swap on the second stage. We have had a clean run through mission milestones so far. It was only 7 or so minutes ago that Electron cleared the pad at LC1, having since completed successful passes through max Q, main engine cutoff and stage separation to reach this point now in the mission. Next up will be the second stage engine shutdown and the final stage separation that will follow the same process as the earlier MECO and separation of the first and second stages. So right now, though, with stage 2's engine still firing, the mission remains on its trajectory to orbit as expected, and all is going well for NROL 199.
FTS is saved.
We are well past the Kármán line now, travelling to this mission's destination in low Earth orbit. When we reach the end of this second stage burn and separate the kick stage, we'll drift along in an elliptical path around Earth before the kick stage's engine lights up and propels the mission into a circular orbit. That happens just moments before payload deployment and the end of the mission for Rocket Lab. From the ground to space and on-orbit operations within only an hour is pretty cool. Okay, so in the next minute or so, we should reach the final acts of the second stage for this mission, the shutdown of its Rutherford engine, called SECO, before the kick stage separates and carries on with the payload. And from there, we'll be ending the broadcast as the mission continues to its classified orbit.
SECO confirmed.
Confirmation from Mission Control that the second stage engine has shut down and the kick stage with the NRO payload has separated. There are still a couple of events to go on the third stage before payload deployment for the NRO. Our third stage will first complete that initial pass of Earth before it ignites to circularize its orbit and bring the payload to its drop-off point in space.
Debris from the tail fin of the trunk section of a SpaceX Dragon capsule has been found on the sheep pasture in the Australian Snowy Mountains. The crash site near the New South Wales rural town of Dalgety matches the orbital flight path of an unpressurised trunk section which should have burnt up during atmospheric re-entry. Chunks of the charred debris, including a 3-metre fin section, were found days after locals heard a loud bang rumbling across the countryside. The trunk section is jettisoned in low orbit before the capsule begins its re-entry phase into the planet's atmosphere, and this particular trunk section would have been jettisoned back in May 2021. It belonged to the Dragon crew capsule carrying the Crew 1 astronauts who had been on station since November 2020. The trunk would have just continued orbiting around the Earth in an ever more slowly degrading orbit, bouncing off the thicker layers of the atmosphere before finally plunging down into it, which is what happened in July. The sheep farmers then discovered the debris when they were doing their local rounds of their properties. After finding the debris, they called the Civil Aviation Authority, that's the Australian counterpart to America's FAA, and they told them to call NASA. However, luckily, a scientist who'd been monitoring the situation, astronomer Brad Tucker from the Australian National University, called the Australian Space Agency instead, and they were able to confirm that the remains were indeed part of a Dragon spacecraft trunk section. And the pieces weren't alone. As well as the two chunks found near Dalgety, a third piece was found further west, near the snowfields resort town of Jindabyne. China is undertaking the maiden flight of a new small payload rocket. The 30-metre tall ZK-1A was launched from the Zhuquan Satellite Launch Center in northwestern China. The new booster replaces the Long March 11 as Beijing's largest and most powerful solid-fueled rocket. It's designed to carry up to 1.5 tons into a 500-kilometre high sun-synchronous orbit and 2 tons into low Earth orbit. For its maiden flight, the new launcher carried what Beijing claimed was 6 experimental microsatellites. Meanwhile, Beijing's launched another 3 Yogang 35 spy satellites from its Xichang Satellite Launch Center in southwestern China aboard a Long March 2D rocket. The trio joined 6 Yogang 25 satellites launched in November last year and June this year. The spacecraft had been placed into a 500-kilometre high orbit. Beijing claimed the new satellites will be used for scientific experiments, monitoring land usage and natural resources. However, what they'll really be doing is providing surveillance and reconnaissance operations for the People's Liberation Army, providing near-continuous high-resolution and electronic monitoring of areas of interest to Beijing as part of the Communist government's preparations for war. China now has an estimated 521 satellites orbiting the Earth. And since 2016, Beijing's launched more than 202 Earth observation, surveillance and reconnaissance satellites, including at least 41 Gaofeng and 95 Yogang spy satellites. This is SpaceTime. That's the show for now. SpaceTime is available every Monday, Wednesday and Friday through Apple Podcasts, iTunes, Stitcher, Google Podcast, Pocket Casts, Spotify, Acast, Amazon Music, Bytes.com, SoundCloud, YouTube, your favorite podcast download provider, and from spacetimewithstuartgary.com. SpaceTime's also broadcast through the National Science Foundation on Science Zone Radio and on both iHeartRadio and TuneIn Radio. And you can help to support our show by visiting the SpaceTime store for a range of promotional merchandising goodies, or by becoming a SpaceTime patron, which gives you access to triple-episode commercial-free versions of the show, as well as lots of bonus audio content which doesn't go to air, access to our exclusive Facebook group, and other rewards. Just go to spacetimewithstuartgary.com for full details. And if you want more SpaceTime, please check out our blog, where you'll find all the stuff we couldn't fit in the show, as well as heaps of images, news stories, loads of videos, and things on the web I find interesting or amusing. Just go to spacetimewithstuartgary.tumblr.com. That's all one word, and that's Tumblr without the E. You can also follow us through @StuartGary on Twitter, @SpaceTimeWithStuartGary on Instagram, through our SpaceTime YouTube channel, and on Facebook, just go to facebook.com/SpaceTime with Stuart Gary. And SpaceTime is brought to you in collaboration with Australian Sky and Telescope magazine, your window on the universe.
You've been listening to SpaceTime with Stuart Gary. This has been another quality podcast production from Bytes.com.